Okay, this is a quick video about a crazy problem involving moving pulleys, one block pushing another block. So as this guy falls, it pulls on this rope, and that rope pulls on this block, which in turn pushes on that block. Let's see how that goes. Something like this. Looks pretty awful. And the goal is to find A. Now I'm going to do this two different ways. I'm going to do it first the boring way with forces and free body diagrams, and then I'm going to do it another way using the energy. And that may be a surprise because normally you use energy to find a half mv squared. In other words, energy is usually for finding v, not for finding a, but I'm going to show you a trick where you can find the acceleration using the energy. It's not taught in most introductory textbooks. It's pretty straightforward, and I don't know why it's a mystery to most people. So I'm going to show you how to do that here. Okay, so let's just get a sense of how this problem works. The first thing to consider that is that if this block moves a distance x to the right, then I create some slack here, and I create some slack here. And what that means is this guy is going to have to pull all of that slack. It has to pull 2 times that much slack. Also, if this block moves to the right x, then this block also has to move to the right x. Those are what are called constraints. So as it moves, the block pulls it, and my constraints are that the little block in the x direction has to move the same as the big block because the big block's pushing it. And in the y direction, in order to pick up all that slack, I have to move twice as far. And I put a minus sign here just to indicate that one moves in what I'm going to call the negative direction and the other is in the positive direction. So, okay, in order to do this problem, we first have to assess what forces are active. I've got a rope, so let me just make it clear there's only one rope here. And so I have only one tension to consider. All the pulleys are massless and frictionless. The next thing I need to do is identify all of the other forces acting in this problem. Wow, that is a lot of forces, totally bananas. Let's look at them. This block, of course, has weight, and there's tension pulling upward on it. This big block pushes the little block to the right, and so the little block, in turn, pushes the big block to the left. This big block has weight pushing down, the normal force pushing up, and then it's got this force up here, which is this reaction force. This pulley's connected via a rod, and normally you might be like, oh, who cares about that? But no, the rope is pulling on the pulley, and the pulley is pulling on the block. And so these two forces are like an action-reaction pair between the pulley and the big block. And then, of course, the pulley is being pulled in two places by the rope. That is a lot, and it is a mess. So let's organize it with free body diagrams. I made a free body diagram for everything that can move. The big block can move, the pulley can move, and M2 can move. So I just organized them that way. The purpose of making free body diagrams is so that I can write equations of motion. That's to say, Newton's second law in each direction. Now, normally I should write M1, A1, but what I've done is I've taken the liberty of eliminating all of the A1, A2s and such in favor of A using my constraints. So I've already done a little bit of algebra when I'm setting these up, and that's why you see over here I have an AY, which I've replaced with a minus M2 times 2A. Now, this is 6 equations and about as many unknowns, and so it's a real headache, but the algebra is not super bad. I'll just show you quickly what you do is you solve this equation for the tension, and then the tension is also equal to N2, and you plug both of these things up here, and when you do that, you end up with an equation that looks like this, and if you solve it, you end up with an equation that looks like this. It's boring algebra. If you want, you can stop and pause the video. I just want you to make sure that you believe me what I do later when I get the exact same result. Okay, so let's park this guy up there. Before I show you energy, I want to show you one other trick to simplify the algebra. Say you still want to use forces, but you're like, ugh, look at all these action-reaction pairs. That's really annoying. Can you get rid of action-reaction pairs? Absolutely. How do you do it? You consider the forces on the system. When you consider the forces on the system, these action-reaction pairs, when they add up, will automatically cancel for you. And so now I'm just going to make one free body diagram, and I'm going to ignore all of the action-reaction pairs because I know that they cancel. So this tells me about the motion of my system. What's my system? Well, it's everything you see here. It's this block, and this pulley. Now, the motion of the system's a little funny because I have motion in the x direction. That's clear what the motion of the system means. But the motion in the y direction is a little weird. One block's moving, the other block isn't. So let's just write an equation in the x direction for our system. And then I'll write an equation just for block 2 in the y direction, since that's the only guy that's moving. And you can see now I have 2 equations instead of 6 equations, and 2 equations is better than 6 equations. These are pretty easy to solve. If I do a little bit of algebra, if I solve this one for t, and I plunk it in over here, okay, then what I'll end up with is, of course, the exact same thing I got before. Okay, so much for that. Now I want to use this energy trick. Okay, so how do we do energy? Well, we write pi plus chi equals pef plus kef. You might say, well, I bet this only works because there's no friction. If there's friction, there's no way you can use energy. Sure you can. I would just include a work done by non-conservative forces right there, and I would do the exact same trick I'm going to show you in 2 lines. It just clutters things, and that's not the emphasis I want. You can redo this problem with friction, and you'll see that it's not a big deal to add it. Okay, so the next thing I do is I write the initial energy of the system and the final energy of the system. You might say, what are you talking about? How could the initial energy possibly be 0? How could it move? Well, the initial energy, nothing's moving, so it's all potential energy, and I'm simply saying my initial height is 0. I can do that because later on I say that my final height is some negative number, and you are allowed to do that so long as you keep it consistent. Okay, now here's the weird thing I'm going to do. Notice there are a bunch of V's here. And I said this was going to be a problem about finding A's, not V's. So how do you get A if you know V? You take a derivative. And that is exactly what I plan to do. I take a derivative on the right, d by dt. I take a derivative on the left. I take a derivative of everything. And the thing I want to impress upon you is that if you take a derivative of v squared, this looks like d by dt of v squared, that's chain rule. So that's the same thing as d by dv of v squared. And then the penalty for taking derivative of the wrong variable is I have to take dv by dt at the end. You can think of, math people will hate this, you can think of the dv's as canceling, and you end up with the d by dt anyway. So in other words, this term, when you differentiate it, gives you 2v times dv dt, and physicists like to write things differentiated with respect to t as a v dot. So this becomes a 2v times v dot, and the dot means derivative. So that's what I've got down here. I've got a 2v v dot. There was a 1/2, so instead of having a 2 and a 1/2, I just got rid of them. And I did that to the second term, and I did it to the third term. And this guy didn't have a v, it just had a y, so I just replace it with a y dot. Now what do I do next? What I do next is I say, okay, well, Vy, I have constraints that tell me what Vy is. And so all I've done is I've replaced the Vy by a 2v times v dot. And then there's one more curious thing I've done. This y dot, you're like, what do I do with that? Well, y dot is the rate at which this thing moves downward. So y dot is the velocity in the y direction. And so I get to make a replacement there too. So the point is, if I clean all of this up, this all equals 0. I end up with something that I can solve for v dot. You might say, wait a minute, what happened to all the v's? Well, look, this has a v, and 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 the whole thing is equal to 0. So I can divide everything by v, and the v disappears. The point is, after a small amount of algebra, I end up with this exact same result that I got before using energy. And you might say, oh, okay, I agree there's fewer equations, but I don't know about this derivative stuff. Well, I want to convince you that this is a sensible thing to do because I'm going to change my setup. Exact same problem as before, only now I put it on an incline. And if you know about forces, now you know that you have to break everything into components. Vectors are an enormous pain in the butt to work with. Every single vector is going to have to now be broken into components, and it's a lot more work. But with energy, it's basically the same amount of work it was before. Now, my constraints are going to change a little bit, so I do have to do a little bit of work on that score. And this is a slightly more complicated setup, so let me use more firepower. I'm going to define a formal coordinate system. So in this formal coordinate system, I'll say that the position of the first pulley is x1, the position of the block is x2, the height of the block is y2, the height of the pulley is y1, and I'm going to say that the width of this down here is w. Why am I doing all that? I'm doing all that because I want to make a claim that this plus this plus this never changes. Each of the individual pieces change, but if the rope doesn't stretch, those all always have to add up to the same amount. And so what did I do? The length of this is simply x1. The length of this one is x1 minus w. And the length of this piece is a little funny. It is the hypotenuse of this triangle. And so this triangle is y1 minus y2. And the base of this triangle is x1 minus x2. Okay, so all this says is that the length of the rope is equal to that. And the other thing is that this triangle is not allowed to make any arbitrary angle. It has to keep the angle of the incline. So what do I do with all that? Well, the first thing I'm going to do is I'm going to get rid of y1 and y2 in favor of x1 and x2. In other words, I take this and I punch it in. Okay, and what do I do after that? Well, I factor out that x1 over x2. That comes out, and I end up with, oh, what the heck? I don't know how that happened. So you end up with a 1 plus tan squared, and a 1 plus tan squared turns into a secant squared, which turns into a secant, which turns into a 1 over cosine. In other words, this horrible looking thing reduces to this. It reduces to this. Okay, so if it reduces to that, what am I supposed to do with this? Guess. Take a derivative. I'm going to take a derivative, take a derivative, take a derivative. That's the theme of this video. I'll end up with 2v1. The derivative of w is 0 because it never changes. And I end up with a v1 instead of an x1. And I end up with a v2. And I put an x there just to be clear that if I take a derivative of x, I end up with the x velocity. And this cos theta, it's constant. It doesn't do anything. And so what does this mean? This means I can solve for v2x. I have just generated from this coordinate system a relationship between v2x and v1. In other words, they're not the same anymore. They have this more complicated relationship. Okay, now I need to find a relationship between the y velocity, like I had in the last one. So what do? I am going to solve this for y1 minus y2. We eliminated that earlier. Now I want to focus on it. And guess what I'm going to do? Derivative. I take a derivative. y1 does not change. Why? Because it's the height of the pulley. The pulley does not move in the y direction. It certainly moves in the x, but not the y. So I end up with minus v2y, and then I have v1 and v2. And the good news is I already know what v2 is, so I can plug in for it. When I plug in, I have v1 minus 2v1 cosine theta with a tan theta. If you clean it up, you end up with v2y equals minus v1, 2v1 sine theta. So let's park those up top. If you found that a little dizzying, I just want to give you one different way to look at it, and this is kind of a relative motion problem. In other words, we say that the velocity of block 2 relative to the Earth is the velocity of block 2 relative to the incline plus the velocity of the incline relative to the Earth. And those are actually easy enough to write. In other words, for this block, relative to the incline, it has to pull twice as much as the block moves. So the block moves forward. Again, that creates slack here, and it creates slack here. And the block has to pull both of those slacks. So that's where the 2 comes from. And then the other thing is, that's in this direction. It pulls twice as much. I just split this into a cosine, an x component, and a sine, a y component. But then the additional wrinkle in this problem, which makes it weird, is that the block is also on top of that, moving to the right. And that's what the incline is doing on top of it. So that's the velocity of the incline relative to the Earth. If you compare what I've got written here to what I've got written up here, they're the same thing. And so I just give that as an additional proof that this is valid, what we're doing. Okay, so the next thing we want to do is let's get back to our energy. Let's get back to energy. Okay, so I'm going to do the same thing I did last time. I'm going to say the potential energy initial plus kinetic energy initial is final and final. Okay, I'm going to do the same trick I did last time, which is to say I'm going to call this 0. And then I have all of these kinetic energy terms. And what am I supposed to do? What I do is I plug in my constraints. I plug in all of my constraints, okay? And when I plug in all of my constraints, then I differentiate. Okay, great. So now I differentiate. So just remember, I just want to be clear. All I'm doing here is I'm plugging in for v2x, and I'm plugging in for v2y. That's it. And then that's my change in energy. I take a derivative just like I did in the last one, and I end up with something that looks pretty messy, but with a little bit of algebra, it can be cleaned up, saying that v2y is 2v1. That's what y dot is, okay? And then if I punch that in, I end up with something that looks like this, which looks quite different than what we had before. But if you clean it up, in other words, if you expand this term and you expand this term, I swear you'll end up with something that looks almost exactly like what we had before. The top has changed by a sine theta. Why? Because the force pulling in this direction is mg sine theta instead of mg. Now, the other thing that's happened is these two terms have been left alone, but this guy has shifted. And this guy has shifted because now the block doesn't push it to the right exactly the same way that it did before. Okay, so that's it. The whole point of this is to convince you that you can use energy to solve for acceleration and hopefully to give you a crack at some of these really crazy block and pulley problems. Okay, anyway, hopefully this was more helpful than confusing.